This lesson is on acceleration due to gravity and freefall. You'll be able to define freefall, state the freefall acceleration of all objects, solve kinematics problems using acceleration due to gravity, and draw characteristic graphs of an object in freefall starting from rest. Gravity is the force that causes all objects with mass to attract each other. It's the force that holds you on the Earth and that makes things fall. And we say that an object is in free fall when the force of gravity is the only force acting on it, when there's no other forces acting on it at all. In other words, there's no air resistance. Near the Earth's surface, objects that are in free fall, that are only experiencing the force of gravity, accelerate towards the center of the Earth with a constant acceleration of 9.8 meters per second squared down. And we use the symbol g with a little vector arrow for acceleration due to gravity. So g is equal to 9.8 meters per second squared down. We also call that free fall acceleration. And therefore, we're going to use that as our acceleration in kinematics equations when an object's in free fall. Just be careful that g is a constant. It's not a variable. Even though it's a letter, we're using it for a specific constant. We're using it to represent the acceleration of 9.8 meters per second squared down. Also note that the acceleration due to gravity does not depend on the mass of the object. All objects, regardless of mass, are going to fall downwards at the same rate if there's no air resistance. Dropping a safe or a washing machine, if that's what that looks like, and a feather on the moon or someplace where there is no air resistance, in other words, when they're in free fall, would result in them hitting the ground at the same time. They would fall at the same rate. The reason we don't see that on Earth is because of air resistance. And we'll explain a bit later in some more detail why all objects fall with the same rate regardless of mass when they're in a vacuum. But briefly, the more massive an object is, the more gravitational pull it feels, and the harder it is to get moving. Those two effects exactly balance each other. Let's use this for a kinematics problem now. A ball is fired straight upwards at a speed of 20 meters per second from a height of 1.5 meters above the ground. How long does it take to go up and come back and hit the ground? Let's let up be positive because it starts off moving upwards. Therefore, the displacement that we actually want it to move in by the end of the question is negative 1.5 meters. It needs to be 1.5 meters below where it started. It starts here, and at the end of the problem, we want it to hit the ground. V1, however, is in the upwards direction, so it's positive 20.0 meters per second. We don't know V2. If we've defined up as positive, then our acceleration is negative 9.8 meters per second squared because it's 9.8 meters per second squared down, and up is positive, down is negative, and the time is what we're looking for. So we take a look at these and we recognize that the equation that we need to use is displacement is equal to initial velocity times time plus half times the acceleration times the time elapsed squared. None of the variables equals 0, and we can't do much rearranging because delta t is what we're looking for, and it appears in two places. In other words, we've got to solve a quadratic. So let's plug our values in. We get negative 1.5 meters equals positive 20 meters per second multiplied by delta t plus 1/2 times negative 9.8 meters per second squared times delta t squared. Got to be very careful about our signs here. Now let's move everything over to one side. We get 4.9 delta t squared. I'm going to drop the brackets. The delta goes with the t, so we know that now. Minus 20 delta t plus 1.5 equals 0. So we've got a quadratic. You could solve this in a number of different ways, by graphing, by using a simultaneous equation solver, by using the quadratic formula, and any of those would give you a value for delta t. In fact, two values for delta t. Rounding to two significant figures, the answers give us negative 0.74 seconds or 4.2 seconds. So what does this mean? Well, this answer, which is not the answer we're looking for, is the amount of time it's taken to get from 1.5 meters below the starting point to the 1.5 meter mark initially. So it's backwards in time. This is the answer that we're looking for. So it's going to take 4.2 seconds for it to go up to the top and come back past the starting point and hit the ground 1.5 meters below. All right, let's talk about position, velocity, and acceleration time graphs for an object in free fall. And we're going to start from rest. Let's put values on our axes. The first one's going to be our position time graph, then we're going to get a velocity time graph, and then an acceleration time graph. Let's just understand the situation. We've got a ball that we're dropping from rest. If we're dropping it from rest, v1 is equal to 0. Also, its initial position is equal to 0, and its acceleration is equal to g, or negative 9.8 meters per second squared. So that's our situation. And we're going to let up be positive. We could let down be positive. We'd get graphs that were vertically reflected. So it might actually be easiest to start with the acceleration time graph, because we know that the acceleration is equal to g, or a constant negative 9.8 meters per second squared. So the acceleration time graph is just a horizontal line showing that at every moment, the value of the acceleration, the y value here, is negative 9.8. Moving up to the velocity time graph, we know that the slope of the velocity time graph has to be negative 9.8 because that's the y value constantly on the acceleration time graph. And we know that the initial velocity is 0. So we start from 0 and we draw a downward sloping line. That's our velocity time graph. Moving up one to our position time graph. Our position time graph is going to look like a downwards facing parabola, like this, also starting from an initial position of 0. If you take a look at this equation, which was one of our 5 equations for constant acceleration, then you can see why that's the case. This becomes 0 in our situation where we're falling from rest because v1 is equal to 0. And a is equal to negative 9.8. So delta x, our displacement, becomes equal to negative, this is a half times 9.8, so negative 4.9 delta t squared. This is displacement, not position, but when we start from position 0, they're the same thing. So this is telling us that in our case specifically, the one we're looking at here, the position is equal to negative 4.9 times the time squared. Now, this is our y variable, and this is our x variable. So it's telling us that we have a downwards facing parabola. So that's just a little mathematical explanation if you want further understanding of why that's a downwards facing parabola. You can also think of the fact that the y values here keep going down, so the slopes here have to keep getting more steeply negative. Let's end with a note about air resistance and terminal velocity. So we've been talking about free fall, or falling in a vacuum, where the only force that's acting on something is the force of gravity. But in air, gas molecules get in the way of a falling object. So here's our falling object. Gas molecules are going to pile up here, and they're going to do that more and more the faster the object goes. That piling up effect increases as objects fall faster. Now, the pileup of those air molecules opposes the force of gravity. They're going to push backwards on the object. They're a form of friction, essentially, pushing backwards on the object in that direction, and that decreases the total acceleration of the object. So instead of falling like it would in a vacuum, it falls more slowly. Though it's not falling as fast as it would in a vacuum, it's still picking up speed. And as it picks up speed, the effect of the air resistance becomes greater and greater until eventually the force of gravity and the force of air resistance are equal. At that point, it's not going to pick up any more speed. It's going to maintain a constant velocity, and we call that its terminal velocity. So objects falling in air are not going to pick up speed indefinitely. They're going to eventually reach a terminal velocity. That's free fall and acceleration due to gravity.